Hi, everyone. Hi, Dan. Hi, Stefan.
Hey, Raja.
Hello. Hi, Rafael.
Oh, hi, Roger.
How's the night been going so far?
Kind of okay. It's kind of cloudy on the mountain.
Okay, we are reading out on red, ready to move. I'm going to send new coordinates to Poco.
Ready to go?
Yep. BHATCY.
Do me a flavor while I'm moving this. Go close the door.
Do you need a -01 there, Stefan? Because it wants 2 digits for the hour. Maybe it's okay.
Oh, I have no idea. Let's find out. I think it's okay, but let's double check.
You know, it says HHMM, that's fine. That looks fine. I bet it'll be the same.
Yes. Okay. All right. PA of 89.
89.
Right in the neighborhood.
There we go. That is not going to be a good guide object.
All right. This is
You may set your slit.
okay.
And you may begin.
All right. Thank you. All right. We'll be here for 10 minutes.
Okay.
Is Stephanie joining today?
Yeah, in a little bit. I think she gets off work right now.
She said at 8:30, so in 2 hours.
Oh, maybe I read that wrong.
Okay.
It could be
Okay.
wrong.
And is Monika connecting today?
I don't know.
Yeah, she said she'll try for the Shadow of the Scientist, but she's not sure.
Okay. And she sent some transient coordinates, I saw.
Yeah,
got
the
the-
first one we couldn't resolve. It was right in the middle of another galaxy.
Got you.
Yeah, middle of the galaxy, and it was kind of cloudy in the area, so couldn't really see the galaxy. Couldn't really see the transient. And if we
I
did, it'd be really high or really low signal to noise. So.
Got you. It's probably a supernova or an AGN if it's in a galaxy like that.
Okay. Yeah, especially if it's right from the middle of the nucleus.
Then it more likely to be an AGN, but Very good, very good. Let's see. This is our last shadow session in the month of November, and then we have a few in December before, for at least for our group, before the semester turns over at the end of January. We'll soon be told how much time we've gotten in the 2023 A semester, which runs from February 1st to July 31st. I'm waiting to hear that any day now.
It's fun.
Could you explain what we're seeing on the screen?
Of course, please. We will do that in just a moment. I was wondering if Rafael, would you, or Stefan, would you like to do that? I mean, I'm happy to do it too, but please take over.
And please don't talk fast because it's hard for me to follow.
No worries. And we are recording this session, so that will hopefully be something you can go back to, and we post our recordings, frequently on our webpage. It'll help us to know what kind of physics or astronomy background, if you have a background in physics or astronomy, please let us know. That'll help us tailor the explanation.
A background?
Yeah, just like background knowledge in astronomy.
I'm not using a background.
No, sorry. I'm saying in terms of your knowledge of astronomy and physics, how would you describe your knowledge of astronomy and physics so that we can explain at the appropriate level?
Unfortunately, I don't really have any good knowledge of the instruments that are used to make observations because I've never had I'm just an amateur
Astronomer.
person who likes it.
Good. This is good to know.
I've never had the opportunity to learn exactly what the various instruments do when you're making an observation. So I don't know what the instruments are doing,
We will explain that. Okay.
Yeah, I'm sorry, 1 second. I was finishing doing something else. Okay. So yeah, what you're seeing right here is basically the viewfinder of our telescope. This is how our telescope operator, I think it's still Dan, yep, is able to, or finds and guides or finds our target, whatever we're looking for. And then he puts it, or what do you call it? He uses this to guide our telescope during our observations.
And if I can chime in for a second, the term guide is a technical term. Guide and track are two technical terms. So basically what happens is because the Earth is spinning, a complete spin every 24 hours, stars in the sky appear to sweep across the, across our field of view. Our telescope is built to track the moving sky, right? So, but it doesn't do a perfect job of tracking. The motors are only so accurate, etc. So guiding is sort of a fine correction where you take a bright star within your field of view that Stefan was pointing to, and you make sure it lands on exactly the same pixels, even fractional pixels, but it's that the center of the star, that the same fractional pixel of the guider camera. And so it makes small corrections to the telescope motion beyond its general tracking motion. So this is called tracking and guiding. Dan, did I get that right? Dan, did you want to chime in on that? Did I get that right about tracking and guiding?
I was only listening with half an ear because I've got
No
Sean
problem.
here that I'm talking to. So
No problem.
The pieces that I heard were broadly correct. There's some technicalities in it that we could get into, but it sounds like the background of the questioner probably isn't too interested in programming and error correction, things like that.
Okay.
Please correct me if I'm wrong, questioner. I didn't catch your name.
Yeah, please tell us your name. We just see the letter M.
Yeah, I'm sorry that I wanted to put my name, but I couldn't seem to get back to that program to
No
put
problem.
my name. Oh, you want my first name?
Whatever you feel comfortable giving us.
Only if
It's-
you're,
yeah.
yeah,
I usually tell people just to call me M because that's my first initial.
No problem. That's fine.
But my name is Marianne, Marianne, Marianne.
Got
Okay.
you. Oh, thank you, Marianne. Okay, so so that's as far as the telescope and the guider camera goes. Stefan, Rafael, do you want to talk about spectroscopy, what we're taking spectra of, what a spectrum is, and I guess, So that-
Sure, you can actually.
yeah, go ahead.
What is that?
yeah, Rafael will explain this much better than I would.
Yeah, what we were looking at in the in one of the that like ICAM thing is the, what is it? Like what the telescope is seeing, and it's a really small square of like what the sky really is, just a huge, like, kind of, you can think of that as a circle. So this is a tiny little square of that huge circle. And you can't see it right now, but there is a slit that runs across this, this little flat thing. And that slit breaks up, well, it doesn't really break up the light necessarily, but it lets in only the light from the little pinpoint of the star that we want to focus on. And then we use that tiny little pinprick of light to pass through some various stuff. You can kind of think of like an old Pink Floyd album where they have that like one white light coming through a prism and then it comes out as a rainbow. We use that in order to set up a little camera underneath that rainbow. And then we, prior to the night before y'all got here, we set up some gas lamps that give off light in very specific wavelengths. And that told us, by taking spectras of those lamps, it told us what wavelengths we're looking at in these spectrums. And then we could point our telescope at various stars and expose for various amounts of time to get enough light to actually see stuff. And you can see that like this long line is the trace of the star that we're pointing at.
That's true. And now when I slide this over it more, I get something called exposure. Whoop, it went away just a minute. Okay, exposure in progress, it says.
Mhm.
Okay,
Yeah.
under control. And it looks like there's something being exposed already.
Mhm. Yeah, so we're pointed at a star and we've opened up the camera to take an exposure for 128 seconds now. There's going to be another 80 or so seconds that it goes. And that basically lets the camera collect enough light and collect enough photons in order for us to actually say, yeah, there's something here, or no, there isn't anything there. Sometimes we have to up the exposure time in order to get more light so that we could actually see what we're looking at.
Yeah, in a little bit, we're actually about to change targets. This is a really fairly bright star, so it's a pretty short exposure. And then
Yeah,
you'll
some
kind
of
of
these
be able to
exposures-
see like the guider cam, and as we find our new target, that'll be kind of interesting to watch.
Okay, and then when we slide over some more, we get
Yeah, so we're using a double spectrograph, which splits that beam of light into basically a red side and a blue side. So you're looking at the red side here, which is from about 5,400 to about 8,800, I think was my 8,500 angstroms. And then on the blue side here, we start at about 3,400 angstroms and go up to about 5,600. So it's a double spectrograph, so we kind of get better data on the blue and the red sides as opposed to right in the middle. And we're reading out on blue, almost done on red. Oh, I need to choose. Sorry, I need to find our next target.
Yeah, so right now what Stefan is doing is putting in new coordinates so that the telescope technician, because we're not there right now, we're at our individual homes. Stefan's right in Hawaii right now, which is very far away. And so they're putting in coordinates in so that the telescope tech can know where to.
Okay, we're reading
move
on
the
red, out
telescope
on
over.
red. Actually, yeah, why don't we introduce ourselves right after this?
Yeah.
But
That's,
yeah,
good
rereading
next
out on
target.
red. I'm going to set new coordinates to POCO. We are ready to move.
Ready to go?
Mhm. Yeah, if you look at this
We are
camera,
Doing at 1843.
want to calculate PA too. You can kind of see the stars jitter around as the telescope moved, but it didn't move very far because we're staying in Andromeda. So, well, we're moving a bit. We want to let
What is
Stefan
this?
or remind Stefan to calculate a PA that helps with the guiding where, as we said, we're taking these exposures for certain amounts of time. And in the time that we start, between the time when we stop, the star has kind of moved in the position of the sky. So we have to calculate this parallactic angle to see how to move the telescope as sky
All
is
right,
kind
a
of shifting.
PA of 84.
So there's a list of objects, and it looks like it's set up to go automatically to each object. Is that right? You don't have to do it. It goes there.
Yeah, usually actually, but this is an old list and we never submitted today's list, so we're just pulling it up off another sheet. But sometimes this allows us to calculate PA and stuff too
And
easier.
it doesn't go automatically though. What
Yeah, you
can
have to
happen? Yeah,
tell it.
yeah.
We have to
Sorry, go ahead.
Submit it to
Because
the telescope
only
text, I
on
believe.
each object for a very short time. So,
Yeah. Some objects we stay on for like 30 to 45 minutes. Some objects it's 5 minutes to just like 3 or 4. Some of the standard stars.
Can I have the slit narrow, please?
Oh, sorry, totally forgot about that. Apologies. All right, and we're looking at 100 seconds.
and then it's okay. There's so many different screens. I can't really keep.
I told you to move. There we go. So the object of interest, you may have just briefly seen it, is in this area here. And what we've done is we've dropped it into the slit, the horizontal black thing you see on the line on the center of the screen. And that is actually the active area of the instrument. And then we were talking about guiding earlier, and you see the green and yellow rectangles moving around. And I am selecting this target over here on the left, the star, to be the guide object. And so the computer is going to try to keep that centered in the green and yellow square. So this is what it looks like when it's expanded. But by keeping that in one place, it keeps the object that's right here in one place. And the importance of that is that if it stays in one place, then all the photons from it are concentrated on the instrument. You may set your slit, by the way.
Okay.
And thereby gives us the best signal that we can get in the conditions we have. And you may begin.
All right, this one's a 1500 second exposure. We'll be here.
20
What was
minutes.
that? 20 minutes.
No, 20 minutes. 25 minutes.
That's not
1500 is
red,
25 minutes.
that's blue.
1600
Yeah,
is
25 minutes. Sorry.
but 1500 is 25. And you've got 1500 or 1600?
Yeah, 500 seconds.
500. Okay.
Okay, and with that, I'm going to be right back.
Cool.
So, sorry, I interrupted the explanation of the science, so I'll mute myself and let you.
Okay. Can't even quite remember what I was talking about. I guess, do you have any further questions? Yeah, right now you could kind of see a little bit before the slit got bigger. Before it was a thin little thing, and that's so that our telescope tech can make sure that the star is right in the middle of the slit, and then we open it back up again to be nice and thick, so that we get the maximum number of light, or I think the maximum amount of light from the star that we could get.
Rafael, I'm thinking maybe worth explaining the Salvation Project overall, sort of taking a step back and what we're doing tonight. I don't know if that hasn't been explained yet, right?
Yeah, I don't think so.
Okay, so just variable stars, transits, Andromeda.
Yeah, this project has a.
Yeah, sorry. I was just going to say we've talked about taking spectra, but saying a little bit about why we're doing this and what information we get from the spectra might be a good way to sort of round up the explanation.
Yeah, this project's name is kind of long. It's the spectroscopic analysis of luminous variables in our neighbor. So yeah, we're looking at
luminous variables and transients in our neighbor.
Yes.
That's the AT
There we go.
salvation. Yes.
Variables and transients salvation. Yeah, so spectroscopic project. We
I'm
want to look at. Thanks, Stefan. Yeah, we want to look at the various components of light.
Do you want me to pull up that slideshow that we made and never used?
That would be great, actually.
Let me
So
find it.
what Stefan has is just a little primer showing what we're doing, why we're doing it, sort of the big picture.
You mean every time it goes on and off, it takes a picture? That little thing on the left, that little yellow square. What is the? Yeah.
No, that's not. It is taking very quick images with the guider camera. And yes, I believe that flashing of that yellow might be each new exposure. But that's not the science frames we're taking. This is just the guider camera that's helping us make sure that the telescope is pointed precisely.
Oh,
Yeah, the guider camera is like a smaller camera that's mounted on the telescope. And
what is the name of the main telescope?
the Shane 3 meter, I believe. Yeah, and then we're using the Kast dual channel spectrograph.
Well, I didn't understand that, but
I'll put it in the chat. I'll write it in the chat.
which observatory are you in?
Lick Observatory.
Okay, that's what I thought. Yeah.
Okay, can you see the slideshow now?
Now I can see a black sky background with the white stars.
That's the Andromeda galaxy. So I'm putting some information in the chat, and Kast double channel spectrograph. I'm just putting the names of the telescope, the observatory, the telescope, and the instrument. I've just put that in the chat, Marianne.
And if Stefan would be kind enough to bring up some of the ham cams, we could sort of show the lay of the land.
Good idea.
Yeah, sure thing. There's a bunch of things all going at once.
Yeah,
Okay, which is this?
I can actually just send a link to the ham cam. So
There we go. Yeah, that might be better too. But here, which is the best one for right now?
Are you actually in the observatory, or are you remote?
Yeah, we're remote, but the telescope tech is there.
You're remote.
Yes, Dan is actually the only one here who's actually in the telescope. Me and Rafael are both working from home. So anyway, I guess we should probably introduce ourselves. Actually,
Possibly.
probably be good. So anyways, I'll go first. My name is Stefan Kimura. I am a graduate of Willamette University. In 2018, I graduated with a degree in physics, and I'm basically working to go back to school to hopefully become an astronomer or do something like this. I live in Kona, Hawaii, or Captain Cook, Hawaii. So it's about an hour and a half drive from the Keck Observatory headquarters, and a 2-hour drive from the summit of Mauna Kea, where there's a whole lot of astronomy going on. So there's a lot of opportunities to work from home or work around home, which would be really nice. So that's working. And I am the newest member of this team, the Salvation team. My job right now is to run the observing nights. I'm the one running the telescope from home, working with Dan, who is up at Mount Hamilton. But it's kind of cool that I can run this remotely through my laptop.
Yeah, where did you say your home is?
I'm in Captain Cook, Hawaii. So on the big island of Hawaii.
Okay. Yeah, one of my daughters is an oceanographer, but she's just getting ready to retire in the University of Hawaii. So.
Yeah, I'm hoping to go attend school at University of Hawaii to get my master's in physics at least, and then maybe my PhD in astronomy or something. But that's that's in process, in progress.
That's nice. You have a lot to look forward to. You have a lot to look forward to, I think.
Yeah, thank you.
Because there are going to be wonderful advances, I believe, in astronomy. I believe in the future, right?
Oh, hopefully, yes, definitely. Okay, Rafael, you wanna?
Yeah, my name is Rafael. I am a graduate student right now at San Francisco State University, working also in astronomy. I graduated like a year and a half ago, I think, from UC Santa Cruz, where I met Raja. I was one of the very first, or few first on the ground floor of this project. I was the first observer, where I was in Stefan's shoes, setting coordinates to the telescope and making sure we're pointing at interesting things. And yeah, we've grown a bit since then, where we've added on Stefan. There's another undergrad, Stephanie, who's working on a double major, I believe, or a master's in addition to her. I can't really remember, but yeah, she's also very good, very smart. Monika will probably be joining in a bit as well. Yeah, I am working on my master's. Also hope for getting a PhD.
Very nice. Yeah, that's good. That's good. And somebody else is sitting. I don't know if this other person is actually sitting under some trees or if that's just a background.
It's a background.
Raja.
I can sit against the ocean. I can sit on the tree. I can sit in front of the Taj Mahal. You tell me what you want, and I will. There we go. There's the Taj. There's the ocean. Now that is a virtual background. So my name is Raja. I'm a professor at the University of California, Santa Cruz, and I work closely with various students on campus and on different research projects. The Salvation Project is one of the projects I work on with Monika, Rafael. Yeah, sorry, go ahead.
Do you have dark skies at that location?
At Santa Cruz, no, because it's a big city, and but Lick Observatory is somewhat removed from the nearest city of San Jose, and it's not as dark as we'd like them to be.
Oh yeah, but you don't. You're not. You're usually at your university, aren't you?
Right now, I'm not at my university. I'm not even at home. I'm in Southern California. I'm going to get back home tomorrow, but I am using the telescope from Southern California, just like Rafael and Stefan and others. So what else can I say? So I did want Dan and Sean to introduce themselves if they have a moment, because they're in the Zoom call link that says 120 ROR. That's the 120-inch telescope. ROR stands for readout room. So Dan, Sean, take it away, please.
Okay, so I'm Dan. This is Sean, who may or may not be in frame. We're one half of the 4 telescope techs that maintain and operate the telescope up here. My background is mechanical engineering. I'll let Sean talk about his in a second. Our job is primarily to make sure that there is a telescope to use tomorrow. which sometimes means that there is not a telescope to use today because we're either trying to fix it or we're protecting it from the weather. The part of our job that we enjoy is interacting with scientists and actually pointing the telescope at stars and hearing what it is that the scientists are studying. But the real reason we're here is in case something doesn't go right, which with a getting on for 60-year-old telescope, 65-year-old telescope is alarmingly common. So I guess I can't complain too much. That's why I've got a job. But that's our primary reason up here. Most of what we do can and is done by computers at other more modern observatories. But there are still people running around on the mountaintop in case things need a little helping hand. I'm happy to answer any questions you might have about the nuts and bolts of telescopes, but I'll shut up for a second and let Sean talk.
I'm a network administrator, network troubleshooter by trade and training. Those skills translated really well to troubleshooting just about any instance that happens here on the mountain. As the decades have progressed, having an understanding of the network does help with isolating issues. And as he stated, our primary role here is to drive and protect the telescope and ensure that the next scientist that comes around has a telescope to use to collect their data.
Well, I think they are still using some of those telescopes for, I believe, for research. They're still using them for research of certain kinds of research, right?
That is correct. This telescope that we're using tonight is 65 years old at this point. And it's still doing cutting edge research. So, you know, can't complain about that. We have other older telescopes on the mountain, and we have a couple of newer telescopes on the mountain. So we're sort of in the average telescope age, if you will.
And you take care of all of them?
Yes. One thing that I didn't hear Raja talk about is we were the first mountaintop observatory and the first big telescope that was deployed as a research instrument anywhere in the world. And it still operates. We used it 3 days ago.
Oh, that's wonderful.
So
I think I was there many years ago, but I was too frightened by that road going there, so I never went back.
yeah, the road is kind of a filter. There are a number of people who say, well, I did that, I don't need to do it again. And it is
Maybe the road is better now. Better.
It's just as curvy as it used to be. They repaved it 2 years ago after the fire we had up here, but it's just as curvy.
But a lot smoother.
Yes, very much smoother. It hasn't got any wider though. I tell you true though, it makes you think real hard about whether you want to run to town to get a cup of Starbucks or not.
Whether what?
Having 45 minutes of curvy road makes you think really hard about going to town for a burger or a cup of coffee or whatever.
Yes. I'm sure it does, yes.
But I will say, having a wife who was pregnant, going through cravings while up here on the mountain, that didn't stop us.
So, I mean, we could go on for hours about funny stories of things that happen on mountains, but I'm not sure how entertaining that would be.
I did want to point out one omission on this slide. Stefan, your name is missing from the slide.
Oh, you're right. That's okay. I'm here.
When you
At
have
this
a
point, I
moment.
think I've mostly contributed to the observations. I haven't done too much with the research side yet.
No,
Still
observations are part of the
catching up.
research. No, when you get a chance, please add your name. Really,
Yes.
you
One second.
definitely belong to
I'm
this
adding
list.
it as we speak.
Good, good
Oh,
for
okay,
you.
cool. All right. Anyways, but I guess we'll talk about the presentation a little bit. So I heard Rafael and Raja explaining what our salvation, what that means, spectroscopic analysis of luminous variables and transients in our neighbor. But we'll talk a little bit more about our telescope first and what we're doing.
Okay, yeah, I think the slides like talked a bit about, so yeah, since we are a study on luminous variables and transients, we want to be able to find these things in the sky. The sky is massive, it's huge. So the best way that we thought about doing this is through the use of these things called large sky surveys. So we have these things called high cadence wide field sky surveys. So let's break that down a little bit. Wide field basically means that the picture is very big. It takes up a lot of the sky. And then the high cadence means it does it fairly often. So we can actually see how the sky evolves over time. And one example of this is kind of the first times that we were looking for exoplanets. We were looking at stars for like changes in their brightness on the scale of like months to years. But it turns out the variability ends up on the scale of days, weeks, months, hours. So we really had to upgrade the cadence of observations. We really had to observe them a lot more often, a lot more frequently in order to actually see how they vary with time.
Yeah, and that means since we're observing it quite often, that means we have a huge amount of data. And from the ZTF, the telescope or the facility we're using to get the data, so we use an alert broker called Antares that it goes through the huge amounts of data that we get from the ZTF and alerts us about objects of interest. Here's a couple of alerts. The one on the left, I believe, is the supernova. Yes, a type 1A supernova. Now we classified, and then the one on the right is a variable star that we just classified as likely a K3 type giant star. That might be in a binary. So we can look at a few other stars. Let me check, make sure our exposure time. Yes, we got a few more minutes. Later, I can show you guys some of the light curves for the targets we're looking at. I have to pull them up right now, so that might take a bit. It's on my other computer right now, but we can look at some of those later. We are looking for basically, since this is a wide field sky survey, that means our field of view is huge, but the magnification, the resolution isn't very precise. So essentially, we can't see it's not a very precise, or we can't see small targets. Let me read these notes real quick.
Basically, I think this slide was getting across that ZTF is over a big portion of the sky, but it's not, again, not very precise. And we really want to focus on individual stars, not the entire universe.
So we find these alerts, and we use our Lick telescope or Lick Observatory and our Shane telescope to take a spectra and look more closely at our targets or objects of interest.
This is just a little diagram of the Shane 3 meter. We use this. I don't know if anyone has ever been to like an astronomy event night kind of thing, but you'll see people with various types of telescopes. There's like the reflectors, refractors, and then for reflectors, you have different types of setups like a Cassegrain or a Newtonian. And so what the Shane 3 meter, what we're using with the Kast dual channel spectrograph is basically a giant Cassegrain telescope. So you can see this picture like this, you can actually see the little ladder down there on the telescope, and that is pretty much to scale, like that's an actual real ladder. So this thing is huge, but because we use this Cassegrain setup, we actually effectively double the path length of the light. And what that corresponds to is a much higher magnification than you would get otherwise. There's a lot more physics that goes into that, but I'm just kind of leaving it at mirror magic. Did you have a question?
So are any of you right next to the telescope at this moment? No, huh? None of you?
Actually, Dan, you can see Dan's name, 120ROR. ROR stands for readout room, and that's because they're right under the telescope where they would read out data if it was actually coming out physically.
So this is not a real-time photograph?
No,
The one showing now is not. The dome is in complete darkness right now. Can you bring up HamCam 2?
Yeah, I can exit this because we're probably actually going to be switching targets soon. So probably a good thing to switch our view.
Yeah, 1 second. Whoop, 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 whoop. HamCam 2.
So if you bring that up full size. So almost in the center of the screen there.
Oh, I scrolled too far. Oh gosh, come back.
So if you click on that again, I could give you a full view, I think. But almost in the center of the screen, there's a big white dome.
Doesn't want
And
to.
that's where I'm sitting. If you look very closely at the base of that dome, you can see a lighted window, and I am right behind that lighted window.
It looks like there are clouds. Clouds.
Yep.
Yeah. If you go back and get the color all sky, there's another view of the dome and the clouds that are directly over us down at the bottom there.
Yeah. Oops. There it's right
That
there.
So at the 10 o'clock point, that's the dome with the 2 windows, and I'm behind the, let's see, I'm behind the one that's lower, closer to the east. And that's updated every 2 minutes. So that's about as real time as it gets. And you can see over in the southwest, the moon is beginning to set. And almost dead center low is Jupiter.
Oh, okay. And I just saw a question from somebody typed in. Somebody typed a question. Can you see the
Yeah.
question?
I cannot. Give me a second.
I know somebody, they probably went on the chat or something and
This is a question from Rob. Says, at the Cassegrain focus, isn't the focal length usually more than doubled by the convex secondary?
It's slightly more than doubled, just because the light path is twice as long. The place where you really get a lot of focal length is if you go to Coudet focus.
Mhm.
Because Cassegrain is literally right behind the mirror. It's maybe 110% of prime focus. It's not a whole lot more. Particularly on this telescope, it's got a sort of inherently long focal length. So going to Cassegrain isn't a big stretch. I hope I've answered that question to your satisfaction.
Yeah, do we actually know the focal ratio of this telescope when we're using the
F5.6 to prime, about F17 at Kast, and about F36 in Coudet.
Wow, very cool. That prime is basically a normal big Newtonian reflector, I should say. But yeah, very
So
cool.
it's the APF, which is the second biggest telescope on the mountain, much newer telescope, I think is what, F2?
That's reflector then.
Yeah, I think it's F4 to Naismith 1. It's a much larger field telescope. This telescope's like looking at the sky through a soda straw.
Yeah, which is kind of what we want. Yeah, we'll be reading down in a minute, so it'd be best to just wait until then to switch back to the slideshow.
Yeah, sorry. I'm also trying to make sure we have enough M31 targets.
Yeah, that's a good move because yeah, we're going to be on M31 until
Pretty long time.
pretty long time. Yeah, another 6 hours. So.
And I kind of feel like, especially with the seeing being kind of bad, I'm looking for more bright. I'm trying to find more bright targets right now.
Yeah, because of all the clouds.
are you seeing spectra readouts on one of your instruments? Spectra?
Yeah, you can actually see the spectrum on the left-hand side, this tall thing.
Oh, there's 2 traces. Huh.
Yeah, there must be a second star or something in the slit.
There,
Noticing.
there are two objects way over to the right at the moment. And after everything gets convoluted, that means way over to the left on the spectrum.
I'm not,
Right.
I don't think,
Let's note that.
I don't know how to get to the spectra.
It should just be on the screen share right now, on the left-hand side of what you're seeing. Oh, went away because I think we're going to switch targets soon.
Okay, reading out on red. I'm gonna send new coordinates to Poco.
Ready to go?
Yep.
Here we go.
See if we can find this one. It's a little faint.
While he's moving, you might want to close up the slit and
Yeah, oh yeah, good point.
And if somebody will calculate a PA for me.
1 second. Making sure this is the right exposure time. Also making sure this is the right target. ABII.
a good thing to confirm.
All right, we're gonna 8 of 107. All right, a PA of 69.
Nice.
69?
Yeah, 69.
That seems pretty far away. Sure that's not 89?
HA 4129. Nope. Make sure I'm sending you the right target. Coordinates are right.
Coordinates are right. We're not that close to meridian yet. You got your exposure correct?
2400 second exposure.
Yeah, that would do it. That'll bring us right up to the meridian.
Oh,
Oh, that
yeah, it's a bit longer, a bit more of a faint target though. So if we can't find it, we have other ones to move on towards.
I think I've got it, but yeah, faint. It is definitely that.
Okay. Oh, actually, yeah, wow. I did not notice, but it went all the way down to 19.01 at some point. 19.87. It's a pretty erratic star.
A lot of dust around it, maybe.
Let's see. I think we've already classified this thing. Let me see.
Okay, so you're gonna have this big bright thing over here on the right. It's gonna go into the slit.
I'm
Do
not
you
sure.
rotate.
Okay, there's some little
Pardon? Sorry.
red square, and then there's this little bright thing.
So our actual object of interest is here in the red square. And the thing that I think is going to cause problems is over here. And somebody decided to move this all around and blind.
Yeah, do you think it might not be worth it, especially with the scene being kind of poor right now?
I'll leave that to you guys to decide. I would, however, recommend a rotation probably clockwise by 15 degrees if we stay.
Yeah, so problem right now is that bright star in the slit would probably mess up the spectrum. Right.
Yeah.
Yeah, I mean, I don't see a problem with rotating necessarily. If you can do that.
I'd be lying if I said I knew exactly what that meant or what the repercussions of that would be.
So that gets into the whole discussion of why we want to do PA. So let me move the tub around so you can see what I'm actually doing. And then we'll have a discussion once the shutters are open.
Oh, okay.
So that's exactly 90. That clears it well and truly. Our object of interest is still half and half in my skybox. That's interesting. I seem to have lost my skybox.
Black and white.
Got an extra marker, so I don't know what happened there. Anyway, you may set your slit.
Okay.
And you may begin. No.
Oh, that's 890. That's not what I want.
Be nice if I could see him.
All right. Starting red. Starting blue. All right. Well, I mean, we can also take a look at the first exposure to make sure we're actually picking up the target.
Somebody just made another comment or question.
Yeah, that is an impressive increase in path length. Yeah, I think it depends on how mirrors are set up that gets you the double Linker ratio. I'm not too recent on the math that actually goes into it, but yeah, I think it's the distance that secondary is. So your secondary is getting you a nice F11 ratio as opposed to your F2 or F4 that would get from possibly putting the secondary at a different spot. That's very cool. Especially cool that you have a 14-inch Smith Cassegrain. I've been, since Black Friday, I'm looking into possibly getting myself a little hobby scope. Jealous of your 14-inch one right now, but it's fine.
The one I
Cool.
really like is my 4-inch refractor, though. It's a really nice one.
Cool. What? Oh, refractor. Yeah. So you have a probably EPO guy, right?
A Takahashi.
Ah, nice. Very cool.
Sorry,
Very
Dan,
cool.
what should I note? How far did we rotate it by?
I took us from 69 to 90, so technically 20 degrees. Probably could have done 15, but I'd rather be completely clear.
Okay.
So to answer the question in the chat, part of that difference in pass length is the magnification of the eyepiece. Especially at Kast, you the ratio of the lens focal lengths enters into that light path calculation. And then to get back to the comment I was making about changing the parallactic angle, what that implies is the Earth's atmosphere is curved like a lens, and therefore it affects light differently according to how much curvature there is, and because it's not a achromatic lens, which is a technical discussion we can have in a minute if anybody's interested. It tends to bend red light more than blue light, and therefore if you have a instrument with a slit in it and you put the slit horizontal to the horizon, you get to choose which wavelength you collect. But if you put the slit vertical to the horizon, you collect all of that and you get a little extra separation in your wavelengths free of charge thanks to physics in the atmosphere. So the ideal case is to put the slit in such a way that it'll be on average vertical to the horizon. But in this case, we had a bright object that was going to swamp the signal from the object of interest. So we tilted it over a little bit to get the bright object out of the way, which means we're throwing away a little bit of that extra spread spectrum to avoid signal and noise problems. So hopefully that was a cogent explanation. If not, ask me questions about the confusing parts and I'll try to clear it up.
Well, that sounds good, but what was causing the bright object?
So that's a nearby star that's brighter than the object that's in the slit.
Oh,
And it turns out that that nearby bright star is convenient for my purposes because we can guide on it. But it would be very hard on whoever has to reduce this data because it would swamp the spectra that we'd get from the dim object with the bright object.
Yeah, so if you hold the slit vertically, you get different amounts of diffraction from the atmosphere.
That is very much the case. In this case, because we're pointed very nearly straight up, the amount of diffraction we get from the atmosphere is very minimal. And so the penalty for not being perfectly vertical to the horizon is very low. If we were down close to the horizon, it would be a much harder choice, how much to move in what direction, and whether or not the gain in signal and noise be worth the loss in spectra.
So what would be the advantage of having it, would you want to have it horizontal then, in this case?
You want to keep it as vertical as possible so that you pick up as much of the dispersed light as possible. In the case where you were looking at something like a galaxy low on the horizon, you would align the slit with the plane of the galaxy, irrespective of the diffraction of the atmosphere or the horizon. It's very much a decide on a case-by-case basis.
Oh, okay. And then do you want to explain the filters?
I'm going to let a physicist do the filters.
I don't know, I just see a whole.
Yeah, we don't do filters.
Something.
They are available. I was paying attention to something else while Dan was giving his talk about the splitting of the light, but my general knowledge of filters is you can take away some light in order to make other light seem brighter on your CCD, because otherwise it might get a little bit too saturated with certain colors. The best thing that I have off the top of my head to explain these are the glasses that can help correct people's color vision. Some people who are colorblind, essentially they're green and blue cones, I think that's right. Their green and blue cones basically can't distinguish between certain wavelengths of light. And so what these eyeglasses do is they filter out those, like the light between those two wavelengths, so that when your eye sees, it's able to more easily distinguish between green and blue, and that kind of takes away some of the color blindness. Very similar idea here. But we don't use any. in our particular program, we don't use any filters. We just want to get as much light as possible. And because variables, like particularly the exotic variable stars we're looking at, we don't quite always know what we're going to get ourselves into at the start of a night. We don't know if we're going to be looking at super blue or super red star, so we don't put any filter on so that we can get as much light as possible from whatever the star is giving out. Yeah, Raja can correct me if I'm wrong here, but I think that's right.
You can change the grading.
Yeah, different gradings can give you different, light will basically split up in different ways. On the red side, we have a grading, and we tilt that grading, and that'll make the light that's split up. You've probably, or you might have played with these in the past, but they're like these little, I actually don't have it on me right now, but there's like these little pieces of cardboard with a little plastic piece of film in between it, and you can pull it up to a light source, you can kind of see like a little rainbow next to the light source. And depending on the light source, you can actually get different colors that it splits it up. And those are diffraction gratings. And that's the exact same thing that we have on the red side here. We have a, not exactly a piece of plastic, I think it's actually a piece of metal that has very specific lines cut into it at very specific spacings. So this, I think, tells us that there are 7,500 lines and they're spaced by 600. I could be wrong. Yeah, but it's essentially telling us information about how many lines there are and how those lines are spaced. And that will break up the light in different ways. And then you can tilt that with respect to the direction that the light is hitting it. And that'll also split the light that comes out in different ways. And so you can set up the grading tilts and the grading to be in such a way that you get the wavelengths that you care about hitting the CCD, the camera at the other end. That's on the red side specifically. On the blue side, we have a thing called the prism, which is a prism which has gratings on it. And it's very similar, except it's a grating, it's a prism with a grating on it, hence the name prism. Yeah. We use this thing called the dichroic to split the light up. So in this project, we use the D57 dichroic, which tells us that as the light comes down, you can actually kind of see this Kast motor control thing. The light comes in and you can see the arrows go down. So it hits Decker first, hits the slit. So the Decker's in spectra mode, and then it hits the slit, and the slit's at 2 arc seconds. It's the upper filter and the lower filter. We don't have any filters, we just leave those open for our project. It hits the wave plate, and then it hits the dichroic here. And this dichroic here splits the light into a blue and a red beam. So the blue beam is anything that has a wavelength that is smaller than 5,700 angstroms, and the red light is anything that has a longer wavelength than 1,000 angstroms. And then it goes back up through the collimator, the filters, and the prism. And that prism is the last thing that it hits before it splits up, and before it splits up and hits the camera. You can kind of see this in the slideshow here, yeah.
Oh, sorry. Yeah, my mic is muted, but yeah, I think
Right.
Rafael explained kind of the different parts of the telescope
Okay.
well, better than I could have. But
Could you leave this
here's a bit of a
diagram?
or diagram.
I'm still looking at the diagram.
Yeah, so the Decker and the slit are up here, and the light comes down. The filters, but we don't have any. And bounces off. Where am I going? Sorry.
Yeah,
I'm trying to
that's
find
a
my mouse.
dichroic.
Trying to find my mouse. And there's the dichroic here. Bounces off here, goes into the collimator.
And that collimator is basically making sure that the light is going in the right direction. Because if it was going offset from this, then you wouldn't be getting a very good picture. So that's a step that we do before you guys get here. We take pictures of gas lamps to make sure that the wavelengths are popping up what they should, and making sure that they're nice and defined when we take the picture, so that it's not all blurry when we're pointing at stars and stuff.
Yeah, focusing the telescope. We had a little bit of a problem here earlier today because it didn't want to move for a little bit, collimator. And I guess Dan was having that problem last night too. So got to watch that. But I think we're good so far.
Yeah, that's good. Yeah, sorry I didn't show up for collimation, and
No worries, no worries.
glad I got.
Can't say it went smoothly, but it went well in the end.
Well, if it was collimated in the end, that's nice. Because honestly, yeah, we set up the collimation to start off with, and then it stays the same throughout the entire night. There are some more sensitive telescopes that will, like, you have to recollimate and focus and take new observations, or yeah, basically refocus the camera every single observation, which is insane to me.
Speaking of which, tell us, did it move? It did. Oh, the blue side moved by 0.007 millimeters. I don't know why, but we started at 23.224 and now it's 23.331. So after this, we should probably change it.
Oh, like tonight?
Yeah, no, it's moved a bit.
Mhm.
That's a pretty significant amount too, because yeah, I started at 23.224. Oh. after this exposure, I need to leave a note for myself.
Yeah.
Reset the blue coordinator. And also check each exposure.
Yeah, I'll put that into the observation log too, that sometime before this, the collimator.
Yeah, no, it was weird because when I was doing or collimating the blue side or focusing the blue side, the decker moved at one point. Like it was in 1 arc second for a while, and then it changed midway through taking or focusing exposures. I don't know what happened, but I had to reset it, so that took a while. Anyways, let's see what else is. Where did my slideshow thing go? Moving forward. So the one who ends up reducing all our spectra is not here right now. Stephanie, she's getting off work in a little bit, but she is the one who does pretty much all the work, taking all of our data and giving us a nice spectra. We usually take our data, our spectra, and if we find something interesting with our transients, we alert the community using ATELs, like the one here on the left.
Well,
Basically.
yeah, what is meant by a rest wavelength? I've never heard that term rest.
Yeah. So
I mean, in connection with the wavelengths, I have not heard that word, R-E-S-T.
yeah, I've talked a bit about taking spectrums of gas lamps. Does that make sense to you? Like, have you heard about taking spectrums of gas lamps and stuff like that before or not?
Yeah.
Okay, yeah, so you know that like if you burn hydrogen, it'll produce emission lines at very specific wavelengths versus sodium, which is a different element. If you burn that, you'll see different emission lines at different wavelengths. The cool thing about waves is that when they are approaching you versus when they are moving away from you, that's a great question. That's a good question for Dan in a second.
What that means is if the object is not moving, that would
yeah.
But if it's moving, it would be different.
Exactly. Yeah, it's kind of like if an ambulance is approaching you, you hear the wee wee and like the noise that it makes. As it approaches you, it's higher pitch, and then when it moves away from you, it's at a lower pitch. Same thing happens with these the wavelengths of light. When a star is moving towards us, the wavelength that it would be giving us for H alpha, for example, here, you can see a blue line at this really sharp peak on the right-hand side. That's H alpha. And if the star is moving towards us, that peak would actually be moved further to the left than where it should be, which is weird. And if you're trying to do chemical analysis, you would not be able to say that that's H alpha necessarily. It would be difficult to say that's a hydrogen feature if you're misattributing it from that little velocity shift. So what people do is that they look at several features like H alpha and H beta, which are the strongest features in the spectra typically, and they shift the entire spectrum based off of those two based off of those two features. So instead of having a velocity associated with the spectrum that shifts the entire thing, you can shift it to a rest frame velocity where all the wavelengths show up and they should be.
Yeah, and if the object is just moving neither just sideways, but not forward or backward, I don't know what would happen.
Nothing. Yeah, that would actually not affect your rest wavelengths because yeah, I don't think that.
Yeah, I believe the term is apparent. Is it apparent velocity moving towards us? Yeah, just the velocity of it moving in the direction of us.
I think that there's also called is it proper motion? Not proper motion. It's
line of sight velocity.
Line of sight. There we go. Line of sight velocity. Yeah, Raja just told me that like 2 weeks ago, and I'd completely forgotten the term already. But yeah, if it's moving left and right in comparison to where you are, you don't see that. But if it's moving towards or away from you, you do see it.
Okay,
Well,
yeah, this diagram doesn't have any units on it.
Mhm.
It doesn't show any, what the units are. But I guess it's, I mean, it doesn't have like 600 or 800 or something.
On the y-axis, you mean?
On the
Oh
wavelength.
no, it's on the top, the observed wavelength.
Since there are no units, and on the vertical, there's no units either. It's just,
The x-axis is actually on the top. The labels are on the top, and it's in angstroms.
it's, you know, it's 4.0 something, but I don't know what the something.
That's a relative amount
And
of
this is
energy. Relative.
I
Oh,
think it's considered flux.
I'm sorry, I didn't see the top. I saw, you
No
know,
worries.
usually things are at the bottom, so I didn't see the top. I'm sorry. But anyway, it still doesn't say what the, where does it say?
It's the relative flux on the y-axis, relative amount of energy. That's why
Yeah,
there's no
yeah.
units. It's a so dimensionless quantity, but on the x-axis, it's meant to show rest wavelength, not the observer wavelength, and that's also somehow cut off here in this.
Yeah, I think. Let's see.
The rest wavelengths are not too different from the observed wavelength because this object is moving
Oh, never mind.
relatively slowly compared to the speed of light.
Or well, no, they would have said that then. I think the spectrum was taken off
Yeah,
of
where's the rest of the
TNS.
spectra?
I want to say it's a TNS spectrum.
Okay.
TNS stands for Transient Network Survey. Is that right? Transient-
Is it spectrograph or survey for the S?
let me see. Check this one.
Something. Let's see. We can pull up some of the alerts later too. Look like the one we're looking at right now, or we were looking at, sorry, earlier today. But anyways,
Transient name server is what it's
yeah.
called. So you can look up an object on this transient name server, and if somebody has posted anything that tells the entire community what this transient is, then it'll get posted to that TNS survey, so that everyone can know, yeah, this point in the sky was definitely a type 1a supernova or a type 2 supernova or a dwarf nova, for example. And then other people can point their fancy telescopes and look at it if they're so interested.
So now
And
you're,
this slide here has a bunch of different images that we've taken. The first three are some of our calibration exposures. So the first one is our arc lamp. So we take a bright light source that we know, or we basically know what the spectra is going to look like, and we take a spectra of it. And this allows us to kind of calibrate our star spectra, or our star spectra, because if we know what wavelengths, where the peaks and or where the emission lines of our exposure show up, and we'll know what exactly the wavelengths are for our spectra when we take it. And Stephanie reduces it. And then we take the bias frames, we turn off all the lamps, close the telescope, and take an exposure. And we use this to basically see if there's any noise, any abnormalities from the CCD cameras that we're taking. And this, so, let's see. And then the next ones are the dome flats. So we open the telescope again and we turn off, or we turn on a lamp with just no spectral features, and take an exposure of that. And we basically see how well the CCD captures the light at all different wavelengths. So we can make sure that no part of the spectra is oversaturating our exposure or anything like that. And then eventually we can take our targets, as you've seen earlier. So we make the slit of our telescope back down to, or very small. And we can point it at one of the, whatever we're looking at, whether it's transient or a variable star. And we take an exposure for, anywhere between 5 minutes and up to almost an hour, depending on how bright our target is. And this line here, our trace, is typically what we turn into our spectra here.
okay, now at the bottom, now I see a lot of little points of light. In addition to the slits, I see
All these little white dots are cosmic rays.
What, pardon?
Cosmic rays.
Oh,
Energetic particles that our CCD camera is picking up. And if you notice, there's a lot more that get picked up on the red side than the blue side. So often we have to take shorter exposures on the red side, so we get less of these cosmic rays. Especially the arc lamp, or especially when we're doing our exposure or our calibration exposures, we usually take about 10, or our exposures are about 10 times longer on the blue side than the red. That's right. Yeah.
Well, do you know why that is on the red side?
I do not.
It's a thicker CCD. It's a thicker silicon device, thickness wise. So it has a greater cross section for trapping cosmic rays. You know, when something is thinner, cosmic ray can pass right through without depositing much energy. Whereas when the CCD is thicker, as it is on the red side, literally the thickness of the silicon has greater stopping power for cosmic rays, so it picks up more.
I'm not sure I understood that, but what is the horizontal line in the target picture?
That's the spectrum of the star.
No, the horizontal line.
Yeah, the horizontal line, that's the spectrum of the star. The vertical lines are glow of the Earth's atmosphere, and the horizontal line is the spectrum of the star. You can see a faint line even in the right spectrum, and it's a little brighter in the left spectrum.
Oh.
And so a cosmic ray is really a high energy particle, and when it strikes a silicon device, it releases it can give up some of its energy to the electrons in the silicon device, release them in the same way that light striking the silicon device can. Now, of course, the silicon device just knows that I've had some energy input and some electrons have been released. It doesn't make a distinction between what type of energy was released. It cannot. It just knows that energy was released. So cosmic rays produce electrons at whichever spots of the silicon device they hit. So does light. Now, because we're pointing the telescope at a particular star and we're taking multiple exposures, the cosmic rays hit different CCDs, different pixels on the silicon device in the, let's say, in the 3 different 10-minute exposures or 3 different 500-second exposures that we're taking. So we can use anti-coincidence to decide that something is a cosmic ray hit versus a spot of light from the star. That makes any sense?
That's interesting.
Yeah, so these are some of the reduced spectra that Stephanie's made. This was earlier observation. Since we have or what do you call our observer? We get basically 2 sides, 2 exposures, the blue side and the red. She has to combine them here, and she stitches the blue side and the red side together into one wave with a wavelength range of 3,500 to 8,700 angstroms. We combine our blue and our red and reduce them. And we can combine them together here.
This was a spectrum of a supernova, I take it?
I have no idea. It doesn't say here. I think Stephanie would know, but she's not here yet.
Okay.
Yeah, sorry.
I think there was just another question just now.
Oh, let me look at that.
Kind of answered it.
Oh,
I was asking what the EWARs do, because they are placed after the CCD. So what do they do with the telescope? I think it's the big vats of like liquid nitrogen that they fill up, and that disperse cold air to the CCD so they don't get too hot.
Oh, yeah. So the Dewar, so Dewar is like a flask, just like a thermos flask, and it contains liquid nitrogen. The CCD is actually inside. Well, the CCD is kept a little bit above liquid nitrogen temperatures, not at liquid nitrogen temperatures, a little bit above. So the liquid nitrogen is used to cool the CCD, and there's actually an active heating mechanism. So you can either drive the heater drives the telescope, the device's temperature up, and liquid nitrogen cools the temperature down. And so it's maintained at a fixed temperature throughout the night, throughout the observations. And this is something that Sean and Dan can perhaps fill us in on about the doer that keeps the CCD. Is there a cold finger that goes into the doer? Is that how?
Yeah,
this is?
there's a copper bar that comes up against the back of the CCD and extends into the doer in hard contact with the doer wall. So liquid nitrogen is actually on the atmospheric side of the vacuum vessel that the CCD lives in. And the whole point of all this, the active heating and the liquid nitrogen, is to, one, hold the chip temperature constant even when the amplifiers run and the chip heats up because you're moving a lot of data through it. But also there is a optimum spot where the amount of read noise you get is minimum and the amount of sensitivity to light is at a maximum relative. Sensitivity goes down with temperature, but read noise also goes down with temperature. And so there's a point at which sort of the sweet spot that you get good read noise characteristics and good light sensitivity. And the object is to hold the CCD at that temperature with active heating and the cooling in the doer. That temperature turns out to be about minus 110 Celsius. See, liquid nitrogen at this altitude is about a minus 198 Celsius. So you can see that there's a bit of a split there.
So it's a little bit more complicated than the piezoelectric coolers that are in the commercial CCDs.
That is correct. The guide camera that you're seeing on one of the screens when we ship targets is actually Peltier cooled, not piezo cooled, but Peltier cooled. And the Peltier coolers keep getting better, and it's likely that the next science camera that we install on this instrument will be Peltier cooled.
Thanks.
I'm just now looking at the supernova one that you have here. Is this something? Is this something you're observing now today, or?
Actually, an old target. I made these slides maybe a month or two ago.
I did get my
yeah.
diagnosis of the supernova right, though, Rafael. It's the same. This is the same spectrum we were showing earlier.
I'm not sure.
It is. If you go back, you'll see it's exactly the same one.
Oh, from that. Yes. Yeah. Yeah, I believe we used a spectrum from a supernova and a variable star in the start of the presentation, and we just kept using the same stars. For consistency.
And in that star spectrum that you see, you can see 3 dips that are near the far right, and those are produced by far right. Those 3 are produced by the calcium, singly ionized calcium atom. So calcium with 1 electron removed from it. The dip at about 6563, that's hydrogen alpha. The dip at 5893 is sodium, so neutral sodium atoms. The dip at 5200 is magnesium. It's actually a triplet. That one when you're pointing to on the there's a set of 3. There's something at 4861, which is H beta, and you can see something at and so on. I mean, there's other lines, but one of the really strong break you can see on a double right below 4000 angstroms, that's produced by calcium H and K, right? That just to the right of that, the doublet to the right of your cursor, that one and the one to the right of that, those 2. That's calcium H and K. And 4340 is that is H gamma. 4101 is visible. That's H delta, sorry, H delta, yeah, that's H delta, 3101. You can see a whole bunch of lines. We should have the participants introduce themselves. That would be lovely, just to see where everyone is connected from tonight. Welcome, Yael. Yael, do you want to introduce yourself real quick? I'm going to pick on you since I know you.
I'm sorry, what?
I have asked one of our participants to introduce herself. Yael, go ahead. Wow, you have a big crowd with you. Yael, go ahead, introduce yourself if you can hear me.
My bad, I was muted. We're having like a SIP movie night tonight.
Oh, wonderful, wonderful.
We're dropping into
A physical movie night, not on Zoom.
Yeah, we've been. Do you know the show Wednesday? Like Wednesday out.
I
I
don't know
just
the
binged
show.
that with my mom
Yeah,
like
we're on, like,
yesterday.
episode 3.
Amazing.
Where are you guys located? Looks like you're outdoors somewhere. It's cold.
Yeah, we're just in my backyard.
Oh, you are, okay.
Nice.
Who's there? Let's see. I can't see people. So tell me your names.
Oh, I'm Flora.
Hi, Flora. How are you?
Good, how are you?
And sorry, who's next?
I'm Connor. I'm Connor.
Connor.
Okay, yeah.
Oh, I'm Wei Jing.
Hi, Regine.
Yes, sir.
Oh,
yeah,
you
did.
did.
Yeah.
Who else?
I'm Amanda. Hi.
Hi, Amanda.
I'm Ryan.
Hi.
Polly has one, yeah. I'm Ryan.
Hi.
Yeah.
Wow, how many
Okay.
people?
Oh yeah, there's a bunch of us.
Wow. So just to explain what SIP is, Yael and the other students who are in her backyard, they were part of a high school science internship program last summer. This is during the months of, it ran from June to August. It's an 10-week program. And each of them was part of the students are grouped into groups of 3 or more, and they work alongside a researcher. So Rafael was a mentor for one of the projects. I was involved in some of the other projects as well. But there are projects in astronomy and a whole bunch of other fields as well, a total of 20 or 21 different subject areas. And so anyway, that's what they represent. Kyle is one of the students, and I guess everyone in that group is a high school student who took part in the science internship program. And let's see, who can I call on next? Rob, how about you? We met in person recently, so let me call on you, please.
Oh, sorry.
Okay.
Sorry to interrupt, but we're gonna head out. We're gonna continue binge watching.
Okay, take care.
series.
Good to see you.
See you.
Go ahead, Rob.
Okay, I'm connecting from Los Angeles. I'm a mathematician, an amateur astronomer, and software engineer. I'm mostly associated with UCLA, but I went to Princeton for grad school, and I found out through Shadow the Scientist through Griffith Observatory. My wife is also here. She met with Raja just a couple days ago.
Hey, Rob.
Tired.
Hi, Stacy.
Hi.
Hi. All right. Let's see. M, would you like to say a little bit about yourself?
I'm sorry, who are you talking to now?
You please, if you would like to, if you want to say anything by way of introduction,
Okay.
please feel free. This is your moment.
I really need to comb my hair, so I think I'll turn this thing off. Okay.
That's fine.
So anyway, no, I'm just a really old person. I hope to become 98 years old in a few days. So,
Wow.
uh,
I think you set the record for the oldest participant in Shadow the Scientist,
Yeah.
if I'm not mistaken.
so anyway, I'm a member of a local astronomy club, which is called the EAS, the East Bay Astronomical Society, which is in Oakland, California. Have you heard, have you heard of the Chabot Observatory in Oakland?
I certainly have. I've visited there as well. That's wonderful. Ariane, how did you find out about us? I mean, how did, I think, was it someone from, was it Andy from Chabot who
Yeah,
spread the word?
somebody sent an email about your program. Yeah, I don't remember
Wonderful.
who it was. Yeah.
I think it might
Anyway,
have been Andy. Yeah.
so they have an astronomy club there, and I used to go to the meetings, but I don't like to drive at night anymore because of my eyesight isn't that great. So the meetings are usually in the evening, so I haven't been going to the astronomy club meetings in recent years, but I still can watch their programs online. I can, since the pandemic, things have gone online. Just about everything has gone online, right? So actually, that makes it better for people like me who don't like to drive at night, right? Do you understand? Did you understand what I said?
Yeah,
Yes.
we did. Yeah, you were clear.
Yeah.
Thanks.
I mean, you people are all young, so you don't know what it's like. But if your eyesight is not very good, it's not good to drive at night.
Of course. Of course. No, we appreciate that. No, thank you for connecting, Marianne. I mean, this is great. It really is great because we've had elementary school students take part in Shadow the Scientist, and it's really nice to see you connect.
Oh, sorry, Roger, 1 second. We are reading out on red
Okay.
about, I'm going to send new coordinates to Poco. Wait, let me make sure red on blue. Yeah. New coordinates to Poco.
Ready to go?
Yep.
Okay.
Get you a PA for this.
Okay, goodbye.
ABLM. DR.
All right.
And I assume somebody's working on a PA for me.
Yep, it is 166.
166.
This is a fainter one, but I figure if we're going to get it, this is probably the best time.
Remember to narrow the slit.
Oh, yep. Especially for a target like this.
Oh, Lord, this thing is dim.
Yes, very. It's like 19-ish.
Yeah.
If not possible, we can move on.
It blinks in and out. It's going to take some doing, but I can get on it.
I think air mass is about as good as it's going to get right now.
Yeah, and the only hope is if it's an emission line object, that we'll be able to get something meaningful. If it's if it's an absorption line object, we'll get nothing useful.
I think even though we've got clouds, I think seeing has improved since we opened. Again, we're going to have a brighter object on the far right of the slit.
Oh, I see it. It didn't seem, it came out very clearly last time, the last exposure. So we managed to miss the other object. Looks like.
The
That's
last
probably because
exposure
the
on-
parallactic angle was different then.
Yeah, I was going to say last.
Yeah, I think we rotated the slit.
Yeah, I mean the
Oh,
parallactic
one,
angle
that,
changes.
that
with
reminds
time.
me, I need, the collimator has moved 0.007 millimeters from its starting position. I'm going to reset that really quick.
Okay. So I'm waiting for a decision, rotate or not rotate.
Probably best to rotate, I assume, to rotate.
Okay, I'm going to give us
Someone
5
with more
degrees.
experience, someone with more experience with me, probably.
I
better
didn't
opinion.
understand the decision point. Sorry, rotate what? Sorry.
So the problem is this object over here on the extreme right
Uh-huh.
at the average parallactic angle
I see.
is in the slit.
You know, it shouldn't affect us. If we'll get its spectrum for free or not, it doesn't matter.
Okay, I just don't want to have your data reduction person calling me bad names.
No, no, they won't. They won't. There's so many pixels from which we can determine the sky that it doesn't matter if there's a second object on there.
Oops. In that case, you may set your slit.
Okay. I guess the question for in the future is like, when would it be a bad time to rotate? When you're looking, when we have a situation like this?
That'd be a Raja question.
What was the question? Sorry, I didn't understand.
So like, when would be a bad time to rotate this? Is there ever going to be a bad time? Like, we don't want to rotate the slit?
But, you know, rotate it, you know, we're not rotating in real time. We're setting it to a particular value and setting it to a value that is as close as possible to the parallactic angle is always a good idea because you want all of the light. You know, basically there's the Earth's atmosphere produces a mini spectrum of the star. It puts a red light at a different location than blue light. It creates it elongates and creates a mini spectrum because it acts like a prism. The Earth's atmosphere does. The vacuum to air interface does that. And you want to align your slit with that little spectrum.
Oh, sorry, Dan, am I able to start the observation?
Sorry.
Am I good to go?
Yes.
Sorry. Right. Sorry, Roger, go on.
No, so when you have such a wide spectral range as we do with this double spectrograph, going all the way from the ultraviolet to the infrared, you are asking for trouble if you don't put the slit along the parallactic angle. You're going to lose light at one end or the other. So you always want the slit at the parallactic angle. Does that answer your question? Yeah, that's sort of what you want to do.
Yeah. Okay.
So to tag on to that question, 2 exposures ago, we had a very bright object that was going to occupy the slit about midway across from the center.
Okay.
Like a factor of 10 in magnitude.
Right there, yeah.
So on my recommendation, we did rotate to keep from swamping the detector.
Got you. Yeah. Look, I mean, yeah, that's, and I assume it wasn't a very long exposure you were doing in that case.
The object
It was a fairly long one, 800 seconds each.
Yeah, the object we were interested in was MAG 18.
Oh, I see.
The
So
object that was, the object we were worried about was more like MAG 10 or 11.
I see. Now, one of the things that's happening, if you're doing 3 800s, which is 2400 seconds, that's 40 minutes. And in 40 minutes, the parallactic angle changes. And so you're observing at some average angle. you're not rotating you're not keeping the slit rotating as the parallactic angle changes. So I guess whenever you're taking a very long exposure, by definition, you're choosing an average angle. So before and after the exposure, at the beginning and end of the exposure, you are losing some light. And that's why in that PA program that calculates a parallactic angle, it asks you how long the exposure is, because it takes half of that and adds it to the current time and calculates the parallactic angle at the midway point of the exposure. That makes sense. So I think you did the right thing to avoid saturation there, but this is in general, you want to stay as close as possible to parallactic. Let's see. We were doing introductions. Can we go back to that? Is it okay to go back to introductions? Let's see, who do I have next on my screen? So we've had Stefan, Dan, go. Okay, I have Annalisa next. Annalisa, do you have a moment to introduce yourself?
Yes, good morning, Kim. Morning, Prof. Annalisa Juste here from South Africa. I was a former master's student at UNISA and also an amateur astronomer and interested in contact binary stars. Thank you so much for a wonderful morning.
Thank you. And UNISA is University of South Africa, right?
That's correct. Yes, it's a what do you call it? Distance learning education institution.
I see. And Annalisa, last night, no, sorry, 2 nights ago, we took a second spectrum of your contact binary, the same one that we had observed before with Demos. We got a spectrum with a spectrograph called ESI that gives full spectral coverage from about 3,800 angstroms all the way to 10,000 angstroms. So we got a second 100-second exposure of that object. And,
excellent.
Yeah, so I'm reducing the DMOS spectra. My student Yuting is reducing the ESI spectrum. We'll send you both as when the spectra are reduced. By reduced, I mean once the instrumental and atmospheric signatures are removed from it, we can send it to you.
Thank you so much.
You're
Just
welcome.
that it might be an interesting object. We don't know that yet, but considering the light curve signature, it's certainly an oddball of some form.
Thank you for connecting again. And I'll go to someone else in Africa. That's Lodrick from the University of Dodoma, right? In Tanzania. Go ahead, Lodrick.
Hello, Roger. How are you all doing?
Good, good. How are you?
I'm good. It's nice to know that there's someone else who has the same time zone as me. Woke up very early. Yeah, so my name is Lodrick. I'm from the University of Dodoma. I have just completed my bachelor's here. In fact, on Thursday is my graduation.
Congratulations.
So, thank you. I am working remotely as a postdoc with the Lick Observatory under the advisory of one of Professor Raja's colleagues, Professor Javier Prochaska. And mainly I'm working on DLAs, the damped Lyman alpha systems. And I am relatively new in astronomy and astrophysics. So I have a background in physics. That's my bachelor's. I took my bachelor's in physics. And so I've just been doing astronomy for maybe, I think now it's about 2-3 months since September. Yeah, so having a lot of fun. I also got a chance to observe with Deimos, I think for 2 nights. Well, that was back in October. Yeah, and back on the point of M was saying something about everything is online now, which is great because if everything was not online, I wouldn't have a chance to work remotely with the Maria Mitchell Observatory, for example. I'll get connected to such wonderful programs like this one. So I love the fact that everything is online now because I don't think I would have to go to America to have this kind of opportunities. So it's lovely that they're available online at the moment. So yeah, thank you.
Thank you, Lodrick. Lodrick, you mentioned that your graduation, is that with a bachelor's degree that you're going to get on Thursday?
Yes, exactly. It's the bachelor's degree.
Okay. And the research you're doing then is post-bac research at Maria Mitchell, right?
Yes,
Got you with Xavier. That's how we got connected, is through Xavier. Very good. Mark, I know you wrote an introduction in the chat. Thank you for doing that. I know Cosmos is a wonderful program. I'm really glad you got to spend part of your summer at Santa Cruz. That was in 2022. Cosmos was back to in-person this summer. SIP will be back to in-person next summer. So that's all. That's great. I'm glad that you're connected. I'm actually in Southern California right now as I connect. I'm in La Crescenta tonight. We're going back to the Bay Area tomorrow. Let's see. Next on my screen, I have another person who's a long time connection to STS, and that's Vicky.
Hello, greetings. I'm late. I'm sorry. I was out doing the terrestrial thing, transplanting plants. I had some help, so I was moving plants around in the garden. Good to see you again. It's been too long. I've missed you,
Vicky.
Yeah, good to see you, and looking forward to December visit and catching up in real time.
Really, we're really looking forward to it. I was talking to my daughter earlier today. She's super excited to come to Molokai. So is my wife, so is my mother-in-law. So really looking forward to it. I can't tell you.
We're definitely looking forward to you. I think quite a few of the kids will be on island. You know, people
Wonderful.
disperse at that time of year. But we're looking at maybe doing a school camp out near where you're staying.
Oh, wonderful, wonderful.
Yeah, that'll be fun. So, so my connection to all this is I'm an educator in a small independent school on the island of Molokai, about 40 students, island of about 7,000. And we stumbled over Raja and through Nakilahoku. And it's just been such a blessing for our students. They've been inspired. They're putting together short videos about something that they wanted to learn more about. So they're doing a production. I'll send some of those. I'll send some along to you.
Thank you, Vicky. That's great. And my one of my former students and he's my current collaborator, Evan Kirby, and I had the privilege of visiting Molokai for our first time, both of us, in September, right before we went to the Big Island to use Keck and Demos. That was just an amazing experience. We spent part of Friday, part of Saturday, all of Saturday on Molokai, and we were so moved by everything there. All of you, Vicky, the warmth of you and your students and your fellow teachers was just something special.
Thank you. Thank you. They figured they're rock stars since they know you, by the way. It's like, it's you have the same status as some of their favorite cultural favorites in music. So.
That's very good to hear. Thank you. I think that's everyone who's. Mark, did you want to speak? I know you typed into the chat, but if you wanted to speak, here's your opportunity. Okay. I'm going to hand it back to Rafael and Stefan to see if we have.
Sorry, Raja, I just have to mention, sorry.
No, go ahead, Lodrick, go ahead, please.
Yeah, so I had a similar experience. So when I saw you joining in when I was observing with Keck, I had just got an email that you were going to do a talk around the same time. So it's a big talk, it's a big deal here, and we have Professor Raja giving a talk. And then I saw you on the observation. I was very excited to sort of just meet you. So I was like, because from where I'm coming from, and everybody was so excited about your talk. I think you did a talk somewhere at the end of October, and then having to talk to you in person was amazing.
Not really in person, right? It's still Zoom, but I know what you mean. I know what you mean.
Exactly.
Real time versus No, it was, I think the talk you're referring to was at the Ghana Planetarium in Accra,
Yes, exactly. That's the one.
where it was held virtually, and I was really lucky to give that talk. And it was I think Sarah Abatsi Masters is someone who had connected to Shadow the Scientist, and she's the one who suggested I give this talk. I feel very privileged because most of the time those talks are given by Ghanaian astronomers. So I was treated as an honorary Ghanaian for that particular talk. So really appreciate that. And Vicky, you connected me to astronomers in Botswana, which is something I'm also very, very grateful for. Lordrick, you're my connection to Tanzania. We have now a connection in Ethiopia, and Lisa's a connection in South Africa. But it all started with a connection in Zimbabwe, actually. And before I had connected to any of you, I had connected to Knowledge Chikundi, who runs the Africa Science Buskers Festival out of Harare. So anyway, there are these wonderful connections. Very grateful for them.
I think Annalise and Lordrick, I have a small business in Botswana, in Mon. Long story. A B&B that's been defunct because of COVID, but I'm trying to get it up and running again. And a long time aloha for that country, maybe 10 years now. I think, maybe someday a trip to Southern Africa would be in order, Raja, and then we could all meet in real time.
It would be amazing. Amazing. That would be great.
That would be lovely. And so I am applying for a workshop in Botswana that's gonna be held next June. So maybe we'll get connected and we'll see.
Stay in touch. I'll be there in June. I teach school in Hawaii, and our school year ends at the end of May. So I'm kind of immediately get on a plane and spend my summer vacation, your winter, in Mount Botswana. So yes, maybe we can do that.
Yeah, that would be lovely.
I'll post my email address. It's no big secret, and then you can get in touch with me and we can figure out.
Oh, thank you. Thank you.
Wonderful. It's nice to see these connections. Really nice to see this. I was going to say that I have a quick question about the science to Rafael and Stefan. I see a hint of a continuum in the blue side, in the red side spectrum. Yeah, I see a hint of very faint continuum. If you change the contrast, there's a way to change the contrast by pick a histogram equalization, HEQ. And you can see the continuum pretty clearly now. Is this one of the spectra of this very faint star, or is this the first one yet to read out?
This is not, I think this is our last target. This is our last target, yeah.
How faint
We
was
haven't
that
gotten
one?
our first one yet. Our first exposure will read out in 106 or 6 seconds.
And how long was the exposure that we're seeing on the screen? And how faint was? Yeah.
The last one we did before this was 800-second exposures.
Okay.
Yeah.
And now we're doing 1,000?
1,000 second, yeah. This is a 19 meg.
And the previous one was 18 point something?
Yeah, the previous one, let me pull it. Actually, let me pull it up right here. I'll show you the Antares link. This is how. Sorry, I'm fighting a cold there still.
No worries.
Oh, no, that's not what I don't want Reddit. Goodness. I realized my laptop screens are two totally different sizes. And this screen
can see
is
your
not gonna
Antares
fit.
window. I can see the Antares window.
Yeah. The problem is it is way too big on my screen, but oh well, that's okay. Here it is.
Okay.
So here's our variable star we're looking at. And then the last alert we saw was at 18.4. But interestingly, this is what I found interesting is I'm not sure if these are alerts or if these are limits. But yeah,
Things
These
there are
are
always alert.
measurements.
Yeah.
Measurements.
And
Oh,
then you
oh,
can-
never mind. It's in the green. It's very faint in the green. Very red star.
I see.
I just saw it first glance. I was like, wow, that's a pretty big difference between measurements. Went from 18.4 to
Yeah,
19.8.
but that's just the color of the
Oh,
star.
different
Yeah,
colors.
two different stars. Yeah.
No,
Yeah,
no, two different filters.
I mean, two different filters. I mean, yeah, two different stars.
Yeah, two different filters. Yeah.
Okay. How do I close this tab?
Yeah, Annalisa, I had forgotten that you found out about STS through Gihan at Botswana, Astronomical Society of Botswana, I think, right?
That's right, Prof. Even last week we had another session that they shared with us. There were some, I think it's a new professor that was visiting, and he did some statistical classification of active galactic nuclei and so on. That was a bit of an academic discussion, I think, so perhaps not as many people might have enjoyed it, but nonetheless, I think we were privileged. We got an invite, and it's also running in South Africa. There are about a few centers here in South Africa that's quite active. So often they get, can I say, academic speakers in, or advanced speakers that can also assist a little bit with the amateur side of astronomy. So it's quite fascinating.
Gotcha.
I'm going to note that. Wait, sorry. I'm going to note that our target is actually the faint trace here, right? Not this bright.
Yeah.
So it's the trace from the center. Yeah, it is nearly non-existent on the blue side and very dim on the red side.
Very dim on the
They
red.
can kind of see
it was a very bright or very dim target, anyways. But we got to note that.
Can we see it at all on the red side?
Bright one.
Can we see it at all on the red side? I'm just curious.
Yeah, like hardly or around the.
I don't see
it.
it.
Right there.
Oh, I see. I see.
Where the cursor is.
Can you crank up the contrast by any chance? No, not that way. I mean, keep histogram equalization, but you can. There are ways you can crank up the. Yeah, exactly.
I am not great with this. How, like this?
Yeah.
Whoa.
Yeah, you can sort of see the trace there.
You can see the trace now, right?
Yeah.
There's something going across the middle there.
Yeah, it's just really
faint.
It's really faint. Yeah.
And again, thanks Stephanie for her work.
Yeah, but you know, if there's any emission lines, it'll. That's our best hope. But I thought I could see something there.
Yeah, that's stuff.
Wonderful. Okay, so this is now. It's now taking 2 more 1,000th second exposures. Then.
Yep, we'll be here. We'll be here a while. So.
Got it. I wanted to check actually something with Annalisa. Do you know, are you connected to the University of Cape Town by any chance?
No, Prof, not at this stage. I'm drifting. What I mean by drifting is I've completed my master's earlier this year, so I'm not enrolled in any with any institution at this point in time. So I'm just doing a little bit of reading up and so on, and then I'll see where. But one big concern is, of course, my location being in Pretoria will make it a bit difficult to be residential at Cape Town. In fact, it will be impossible. But I did contact them at one stage, but they haven't reverted as yet.
Okay, I visited them years ago, many years ago. This would have been around 2006 or so, about 15 years ago. I visited, and I'm trying to remember the name of the person. There were a couple of people I spoke to. Patricia is her first name. Whitlock, I think, is the name of her last name. She was my host when I visited. I gave a talk there. I'm just curious if you know anyone who is connected to researchers, either at astronomy researchers at UCT, University of Cape Town. Please let me know. Please connect them to me, because it would be nice if, when they're doing observations with their telescope, if they would consider hosting an STS session.
So Raja,
I hear what you say.
Yeah, I have a connection to the Northwestern University in South Africa with a professor known as James Chiweze.
Okay.
So maybe I'll talk to him about STS.
Because the concept is very simple, as you can see. The scientists who are doing the work are connecting on Zoom, sharing their control software. Tonight, Stefan is sharing his screen, and it's really explaining what we do. And the idea is to make it very simple for people to host and to make it simple for people to participate as guests. The idea is simplicity, really. The simplicity is our goal here. So, yeah, thank you. Any such connections would be greatly appreciated.
Okay, I'll shoot him an email and then I'll CC you.
Thank you very much. And Stefan, I'm not bringing my tennis racket, but I'll bring my sneakers. I'm looking forward to playing tennis with you when I'm on the Big Island.
Yes, sounds good. Sounds good. I'm excited.
HPA indoor courts or somewhere in Kona, whichever's closer. I'm actually going to be very close to you.
Yeah, probably since you're staying near you said you were staying near Kahalu.
Yeah, we're not far.
My
from
home
there.
courts are less than a 5-minute drive from that place, so perfect.
Okay, great.
Yeah, the coach at HPA is a little upset with me right now, so I don't know if he'd want me playing on their courts.
I used to play with the Keck staff when I go to Waimea. But yeah, I know I won't bring a racket along, but I assume I can borrow one.
No, we have rackets for you.
And I might try to tempt my daughter and wife into playing as well.
Yeah, or pickleball if not. Pickleball
would be amazing. Yes, pickleball would be amazing. You play both?
Yeah, I mostly play pickleball at this point. I'm too lazy to play tennis.
I would love to play pickleball in that case.
Yeah, certainly.
I haven't played much. I've played once or twice, I think. But it's
easy enough.
Exactly.
Very easy enough to pick up.
But I play a lot of table tennis and I play a lot of tennis. So not a lot, but I play tennis and I play a lot of table tennis. So it should be easy to pick up.
Yeah, it'll be easy for you.
I guess it's very similar to table tennis in terms of a paddle and a ball, right? There's no strings. No strings attached.
Yeah, there are even some pros who've transferred from ping pong who hold it the funky way that ping pong players hold their paddle.
Really? Pen holder grip?
Yeah.
Wow, that's very strange.
There's some, I don't know what to call it, but they hit pickleball. They play pickleball like that.
It's called the pen holder grip, but that's a big paddle to be holding that way. Wow, it's crazy.
Yeah, it was like they must have really strong wrists.
Yeah, it has strong wrists.
Flick it at that rate.
Wow. Okay, how are we doing on time? Let's see. We are actually at the closing point. Wow, my internal clock must be very good because it's exactly 2 hours into our Shadow the Scientist session. So I'm actually going to stop recording, but we can continue. You can remain connected. Any closing remarks before I stop recording? Anything else anyone wants to say, or any comment or question? But you're welcome to stay on. You don't have to leave, but I'm just going to stop the recording. Thank you again for an excellent STS session. It's it's really exciting to have people from all over the world connected. It's just fantastic.